All right, welcome to our first video tutorial of what we did last class, just giving it a shot to see if we can put it up on our online classroom and then see if we can keep this going. All right, so last class we introduced the concept of gravitational fields to our higher level class, and we focused on the first topic, which was just describing what field patterns look like around source masses, and all that information can be found on page 396 of the SOCOS text. All right, so field forces are a type of force that act over a distance. They don't require any contact at all. It's a very special type of force. It's kind of magical. We talk a lot about it in Star Wars, using the force to move things at a distance. And in reality, we have only two types of forces in our nature that do that. They're gravitational forces and electrostatic forces. Okay, but we're focusing for the first part only on gravitational forces. The second half of the chapter does electrostatic forces. So if we look at the equation of gravitational forces, we see that the force of gravity is directly proportional to the product of the masses and is inversely proportional to the distance separating that. Remember that? That's what I called, that was the Newton's universal law of gravitation. We had to memorize that definition. We practiced it last class. And we got to remember that G is equal to 6.67 times 10 to the minus 11. But you need to figure out what the units are. And that's something that we did last class, and I want you to try to figure that out. What would the units of G be such that we can cancel things out and end up with the product being in newtons? And the product needs to be, well, it needs to be either newtons or it needs to be kilograms meters per second squared. So what would that be? How would you be able to solve what the units for G are? That's something that you always have to do when we're looking at constants. We have to be comfortable trying to figure out what the units are, and I'm going to let you try to figure that out on your own, okay? If we look at the formula for electrostatic forces, it looks very, very similar, except the letters on the numerator are different. K, on that hand, is a different constant. We did that last year in grade 10, and that's Coulomb's constant, which is 8.99 times 10 to the 9. You can see that between the two, G and K are very different. Electrostatic forces are actually, I don't know, it depends, but they're quite strong in comparison to gravitational forces. And so that's something we'll talk about a bit later. But Q in that formula is the charge of an electrostatic charge. R is the distance separating it. And what you'd notice between both formulas is that the denominator is R squared. And that's what we call the inverse square law. Okay, so that's very important for field forces. They all obey the inverse square law. Okay. So the inverse square law states that the forces that act over a distance, non-contact forces, they diminish by a square of the distance. So they rapidly decrease in strength. On the other hand, as you get closer and closer between objects, the force gets exponentially stronger. That's an important thing to know. Okay, so those are the two formulas that we've already come across, the one last year and one this year, and we're going to try to figure out a little bit more about how they're applied in this higher level section. So moving on. What are force fields? Well, force fields are fields that are centered around objects of mass or charge that emanate a region of non-contact force. Okay, so if I place an object, let's say this little bowling ball in outer space, okay, immediately once I place that object in outer space, it's going to emanate a field. And if this is a mass, okay, a point mass, it emanates a gravitational field that attracts any other little point mass towards it, okay? And so that little point mass is going to be attracted to the center of mass, okay? So what it'll look like is that it'll be attracted to the center. If another point mass was here, it would be attracted to the center. If a point mass was there, it would be attracted to the center. Okay, and if I went all around this object drawing little point masses, I can map out what the field is going to look like. Now you can't see the arrowheads. The arrowheads are inside of that bowling ball. They're all pointing towards the center. All these arrowheads are showing the direction that a test mass is going to fly if I placed it next to the bowling ball. Now, why does it fly? Why does the smaller little point mass fly towards the center of the larger mass? Well, the smaller mass is going to experience the equal and opposite force, but it's a smaller mass, so it's going to experience a greater acceleration than the bigger mass at the center. That's why the arrows are pointing towards the larger center mass. It apparently doesn't really move as much in comparison to the smaller point masses. So if I have placed an object anywhere around that larger object in the middle, it's going to experience a force because it has entered the field, the region where the non-contact force is acting. Okay, and we can draw those forces. So I'll do that again. If I draw an object, I can map out what the force would look like. Okay, so if I drew an object, I can map out exactly what the force would look like. It's all pointing towards the center. If it's a flat object and I'm very close, the field forces would look much like that, because if I placed little test charges there, they'd be attracted to the larger mass plate and fall straight down like that. So these little arrows are showing the direction of the force, and those arrows are called field lines. Okay? So when we talk about field lines, show the direction of field lines, show the spacing of field lines. That's something I'll talk about in a second, but you'll understand a little bit more about how to interpret the direction and spacing of field lines to talk about the strength of forces experienced by it. Okay, so objects that enter the field of space will experience forces that become exponentially stronger as they approach the mass or charge emanating the field. So as we get closer and closer and closer, that force gets exponentially stronger because of the formula that we just presented before, and more importantly, the inverse square law. It says that as we get closer and closer and closer, that force is going to get exponentially larger. All right, so how do we describe field strength? Okay, in the last equation, we can describe the force of gravity in a field, but how do we describe what the field strength is? So gravitational field strength is defined as the force experienced per unit mass of an object positioned at a specific point in a field. Its units of measurement are therefore newtons per kilogram. Okay, so field strength is force per unit mass. Okay, if I take gravitational force formula, Newton's universal law of gravitational force, I can rearrange that equation to get a gravitational field strength. All I have to do is move the test mass. Okay, m1 would be the larger mass, so the mass of the Earth. m2 would be an object on the outside of the Earth. If I move that over, I'll be able to then get what the gravitational field strength would look like, or the magnitude of it would be at a specific position in a gravitational field. R means the position in the gravitational field. So the force per unit mass is equal to G m1 over r squared. Okay, so G m1 over r squared, as I presented in class, actually has a symbol, and the symbol of that is G. We've been using that all along. We talked about that last class where we said that G, as we talked about it in the mechanics unit, is the acceleration of gravity, but it's actually the gravitational field strength. And G, according to this formula, changes. It's not always 9.81. It changes as a function of distance. The higher we go above the surface of the Earth, G is going to change. And according to this, it actually gets smaller. So if we were on top of Mount Everest, as I said in class, the G value there is going to be like 9.6. That's what Malte calculated. So we can actually see that the acceleration of gravity gets smaller, but it's also because the gravitational field strength also gets smaller as we separate the masses. Okay, so how do we draw gravitational field lines and interpret their strengths? Well, as I showed before, you draw field lines by putting test masses and drawing how they would drop towards a mass. So what I've drawn here is objects that are relatively close to the surface of Earth. Okay, so if when we're close to the surface of the Earth looks flat, all right? It's not curved. So if I place objects across my room, as I told you in class, they're all going to fall exactly straight down. And the spacing between those field lines, that's really important. They're all equal spaced. When the spacing is equal spaced, we can say that the gravitational field strength is uniform. Okay? So G is uniform. I have a uniform gravitational field strength if they're all spaced equally. But if I went further away from the Earth, okay, now the Earth becomes curved. Okay, and if I put test masses around there, as I drew in class, okay, all these test masses are going to be attracted to the center of the Earth. And I'm drawing what the field looks like. And what you can see is that these field lines, they get congested. They get really close together as they're getting close to the surface of the Earth. But as we're farther away, the field lines are further apart. And this is like a cartoon image that allows me to interpret qualitatively what the field strength would look like. As these lines get closer and closer together, the field strength is strong. As they're further and further apart, the field strength gets weaker and weaker and weaker. So that's just kind of how we can interpret the strengths from the drawings. Okay, so remember when you're making a drawing, you take the test mass and you draw an arrow showing the direction that it would be attracted. Remember that they're always attracted to the center of mass of an object. When we're close to the surface of the Earth is flat, so we're always being attracted straight down, but when we're further away, we're attracted to the center of a circle, and it forms this radial pattern that you see there. Okay, how can we calculate gravitational field strengths of planets? Okay, well, using the formula that we just derived, G is equal to capital G mass of the planet over r squared. Now r squared would be the radius of the planet, or the distance from the center of the planet that we are. So that's the formula that you would use. G is a constant, so if I found out what the mass of the planet actually was, or the mass of the object I'm looking at, and I knew the radius separating it, I can easily calculate what the gravitational field strength is, okay? Or if somehow in a question they gave you the force experienced by a unit mass, then the force experienced by a unit mass is also equal to G, okay? So those are two different ways that we can calculate the acceleration of gravity. In fact, for Earth, that's kind of how we did it. We were able to discover the mass of the Earth by measuring the acceleration of gravity, and we were able to do a few other experiments hundreds of years ago to determine what the radius of the Earth was. So we were able to apply that to be able to calculate the mass of the Earth. A very cool experiment that was done, wow, like thousands of years ago. It's pretty neat. Okay. So last thing I wanted to talk about is if I was going to map the gravitational field strength versus the distance from a planet. So say here we are, we're on the surface of a planet, and we want to get away, all right? What would the gravitational field strength look like as we are getting further and further and further away? What would the graph look like? So I have a graph that looks like this. And I would think that, well, gravitational field strength is F over m, which is going to be equal to G, mass of the planet, divided by r squared. Okay, well, this makes sense. The mass of the planet times G. Okay, the smaller the r, the higher that gravitational field strength should be, right? And the further away I get, it starts to drop exponentially. So I would imagine that the gravitational field strength versus distance. Now, I want to do this right. I need to have my units. Okay, and this is going to be newtons per meter. Okay, should look something like that. Well, in all reality, that's wrong. It doesn't look like that. Gravitational field strength is an attractive force. Well, gravity is an attractive force. So the force of gravity is actually negative. So my gravitational field strength good question. My gravitational field strength would look like that. The more negative the force, the more attractive it is. Okay, so my gravitational field strength goes from negative, once my gravitational field strength approaches 0, then I have no attraction whatsoever. Okay, so that's something to research. Sometimes we'll see the gravitational field strength as positive, but in that case, actually gravitational attractive forces have a negative force on it. That might not be right. I'll get back to you. We'll see if that's right or wrong.